All right, so let's estimate our area using R6 from x equals 0 to x equals 3. I'm going to estimate the area under the curve from x equals 0 to x equals 3 using this, what we call R6, which means what? Right-hand endpoints, 6 rectangles. Okay? So our area, approximately R6, equals, well, it's going to equal, board shaking because they're walking up there. Okay. Okay, so we've got 6 rectangles. We're going from 0 to 3. So what does that mean as far as the width of each rectangle? It's going to have to be a half, right? Delta x, we call it b minus a. So I've got 3 minus 0 divided by 6 rectangles. So you got 3 over 6, so you get a half. So yeah, each rectangle we're going to have at a half increment here. Oh, oops, went too far. All right. So what's R6? Well, we got this one. This one we don't know the function, so we just have to use the graph. What have I got for height there? It depends on what moment I choose there. Sometimes it's here, sometimes it's there. Okay. But anyway, the height, what does it look? You tell. About 2.1. Okay, so the first one I've got a half by 2.1. Did mark how far I can go here. Too far there. Okay. I'll go over here. Let's be right there. Okay. All right. Second one. Well, it looks to be just a little bit off. So of the x-intercept. So it's a little half, maybe. So it's a half by a half. You okay with that? Now, here's why I bring this one up. What about the third rectangle? Well, the third rectangle is down here. How? Well, it's half wide, but whoops. What about the height, or the width, or the length, or whatever it is we're talking? It's a negative, isn't it? This one's a negative. Well, I keep it a negative because, yeah, the function really decides, what your height is. And in this case, the height is actually below the x-axis, so that's going to mean it's going to be a negative. And that we keep it a negative. We do keep it a negative there. All right, so that's what, a negative 2.5? Is that what you said? Huh? 2.1, 2.5, something like that. Okay, we're going to talk about it. We're going to talk about why we keep it negative. Because one reason we keep it negative, like I said, is because the function specifies what your height is. And in this case, the height's below the x-axis. And when you're doing these areas, below the x-axis is significant. We don't want to change it to a positive. Now, there are some cases where we would, but not in this case. If it's a negative value, we want to keep it as a negative value. Okay? All right, and so then the fourth one is what? I get it about the same as the third one, so whatever you chose there, I say it's negative 2.5, but could be slightly off of that. Now the fifth one, we're back up above the x-axis, right? By my calculations anyway. Maybe slightly different on yours, but yeah, it looks to be somewhere above the x-axis. I'm going to say it's about 1.1. And then the last one is, well, it's way up there, so it's a big, tall rectangle. So yeah, that's 10. Is it 10? Right at 10? Oh, yeah. I shouldn't have stopped it there. It continues on. This is just a polynomial function. So, okay. So altogether there, yeah. Of course, these are going to give us negative values, and that's perfectly fine. Like I said, it's it's going to counteract, if you will, the positive values. So we're not going to get, if everything was above the x-axis, we get a bigger number, but some are below, so those are negative. So what do we get? 0.5. And then we got, what, 2.1, 0.5 again, negative 2.5, another negative 2.5, 1.1, and 10. I get that to be 4.35. R6 is 4.3. Anybody else get close to that? I mean, if you use slightly different numbers, it'll be slightly different. This is just an estimation. Okay? All right, so yeah, from what we observed there, since we're using function values, those negative values have to stay in there. And so hence, we described it earlier as area. We're trying to estimate the area under the curve. However, that's not entirely accurate to say area under the curve if we have negative, if the curve drops below the x-axis. Because if we're talking under the curve, that would mean over here. So it's more accurate to say I'm focusing in on the area between the curve and the x-axis. I think I said that some. We shortened it to under the curve, but we're talking about the area between the curve and the x-axis. But that's not entirely accurate either, because yeah, these areas are negative, so they're counteracting the positives. So why don't we call it the net area under the curve? Because what that means, right, is if I've got more above the x-axis than below the x-axis, it's still going to come out to be a positive number. However, if there's more below the x-axis than there is above the x-axis, what's going to happen then? You're going to have a negative value. So it's a net area. It's kind of the difference between the areas above the x-axis and below the x-axis. So that's more accurate to describe when I'm using these rectangles with the curve, is to describe it not just as area, but or think of it as net area under the curve. Net area between the curve and the x-axis. Yeah, because this area on the top, the areas here, those are going to be positive values, but the area down here is going to be a negative value, so you have some give and take there. Okay, so that's a very important point to note here, that yeah, when we calculate these rectangles areas, sometimes we'll get some negative values, and so we're factoring that in. Okay, now let me get. I don't have to turn that off. Let's turn this off. I'm going to turn these lights back on. Get ready. Turn this off for a second. We'll come back to the handout hopefully in a second. Fourth time's charm. Okay. Yeah, some notation here. If I do a right-handed endpoint sum, just in general, call it R sub n, meaning right-hand endpoints in rectangles. I have this. It all sets up like we were just doing. We have the delta x times what would be the first height. Well, it's f of x1, whatever the first right-hand endpoint is, right? It's, if I've got this curve here, here's A to B. Yeah, the first one is there, right? x1, that's my first endpoint, right? The right endpoint. And then the second one would be f of x2. So it'd be delta x times f of x2, because the delta x stays consistent there. Delta x times f of x3, dot, 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 until we get to the last rectangle, which the last rectangle will be delta x times what? F of x sub n, wouldn't it? If I'm doing n rectangles. If I was doing 5 rectangles, it'd be f of x5. So whatever n is, f of x sub n is the last height. Everybody okay on that? Here's the notation, though. The notation uses the sigma notation, the summation notation. Anybody familiar with that? The sum symbol. Because here's really what I'm doing is I'm doing a repetitive thing over and over again. I'm taking delta x times f of x whatever x is. Well, here's how I can denote that. If you're familiar with the summation notation, or if you're not, here's what we can do. I can condense all this into this sigma notation. Sigma, this Greek letter sigma, you know what it means, right? Summation. It means sum the values. If you see the kind of the pi symbol, that means times, but you don't see that. But anyway, this is sigma, summation. Sigma, the Greek letter sigma, the funny looking e, is summation. So this is saying sum all these delta x times f of x sub whatevers, and then the I is the index. I is saying run from 1 to n, and that's exactly what I did, right? Run 1 to n, 1, 2, 3, 4, 5, all the way to n. That's what I is doing. So it's just a shortened way of doing it. Condensing. Huh? You can call it J, you call it K. I is just kind of like we use X for the variable, we use I for the index. But yeah, sometimes you'll see J for the index. So we could do the same thing, J to 1 to n, X sub J. But usually it's I's to start off with. Okay? Now, also, so that's one way to condense it, to write these all down at once, if you will. Also, this is known, all this summation, these are known as what are known as Riemann sums. These rectangle areas are also referred to as Riemann sums because they're sums. Riemann for a mathematician of long ago, but called Riemann sums. Also, one quick note here, we also might see, couldn't I just flip-flop those? This, usually more often, we start out doing delta x, f of x, but usually more often you'll see it flip-flop there, so it's the same thing, right? Multiplication is commutative, so we can commute those around. That's probably more how you would see it, though, the f of x sub i's times the delta x's for different reasons. Okay? So, if I see this notation here, what does it represent? What does this represent? Area under the curve. But what if you have some negative values? Net area. Okay. Yeah, if we see this notation here, f of x sub I times delta x, the sum of all those, remember it's the net area. Net area under the curve. Using some latitude there, because technically it's not under the curve, it's between the curve and the x-axis, but it's just easier to say under the curve, and you know what we mean, okay? And it's a net area. So that's what that means, and that's... Now, what if I use midpoints instead of right endpoints? Well, if I go in here and use a midpoint instead of a right endpoint, what does that change? Instead of using the right endpoint, it changes the x value. It changes this value. Does delta x change? No. Delta x is staying the same. What changes is this value. Now, I don't know if you've seen it before, but usually for midpoints they use a little bar over it. like if you want the midpoint of something, you put a bar over it. And that's one way we could do it. I don't know if they do it much here, but call it MN, midpoint N, okay? That would be the sum then of this I 1 to n's, delta x times f of the x sub I bars, which just means the midpoint in your ith interval, or if you're in your first interval, it's the midpoint of the first interval. Okay. So instead of x sub 1 for this one, we'd be doing the midpoint at x sub of the first interval. Call it x1 bar. Okay. So yeah, this, if I change it from right to midpoint, and then if I change it to left endpoints, what's going to change is this. So sometimes the way they do it in general then is they write it this way. This Riemann sum in general. Because this value, it could be x sub 1, it could be the midpoint in the first interval for each one. It could be the left endpoint, which, that would be a whole other thing. But in general, here's what we can say. The Riemann sum that estimates the net area of the curve, in general, let's do it this way. I equals 1 to n. Delta, let's do f x sub I star delta x. X sub I star. And I saw where in the homework they use this terminology. X sub I star is just whatever sample point you want it to be. Whether you want it to be left endpoints or right endpoints or midpoints. The star just indicates use whatever you want to use, but we could use different things. We could use 3/4 points. That'd be fun, right? Do the 3/4 point in each interval. You could do it. May not be that fun. But actually, if you found the first one, then you just do delta x plus the rest of them, right? So it wouldn't be that bad. But anyway, yeah, so x sub I star, that's just a general notation for a sample point. Sample point in the ith interval. Ith. Okay? Oh. All right. When they go off. All right. Now, one other quick point before we move on here to the next. All right. What if, we're talking about this is approximating the net area under the curve. What if I wanted the exact area under the curve? Well, we talked about that, the exact net area. Okay, I'll keep that in mind. So here's my A, here's my B. Yeah, with the rectangles, we get the approximation, here, 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 whatever. We get that approximation. But what if I want exact area? Well, I keep doing more and more rectangles, right? I do 12 rectangles. I do 50 rectangles. I do 1,000. Well, what am I doing? I'm making, on this Riemann sum, I'm making n larger and larger and larger, right? So if I could somehow run n to infinity, wouldn't that get us a pretty good rendition of the area? Yeah, if I have infinitely many rectangles here, they're so very small, I can't even see how the difference between one strip to the next. They're infinitely small. So if I have infinitely many rectangles, that'll get you your exact area, right? under the curve, between the curve and the x-axis. You know the drill, okay? Well, how does that represent, how does that look in this Riemann Sum notation? So what we're saying is, not approximately equal, the area equals, if I could run these to infinity, I get myself the exact area. I wouldn't be able to see any little edge that's not matching up with the curve here. I get the exact area. Well, how do I do that? Well, like I said, I want to run n to infinity. Why don't I do this? If I could calculate the limit as n goes to infinity, wouldn't that give me infinitely many rectangles? If there was some way I could look at the limit of this, yeah, that's what we're going to do in a day or so. Okay, I guess since we don't meet Friday, it'll be a few more days down the road. But anyway, yeah, keep that in mind. So this gives us the exact area. If I put this limit n goes to infinity, that's going to get me my exact area. Because there's no way to do infinitely many rectangles, but we can do limits, can't we? We've been doing limits quite a bit. And we'll see where we go with that, like I said, in a day or so. Okay? All right. Let's do a couple of others. We'll go back to approximating for a second. All right, so let's say evaluate the Riemann sum for f of x equals x cubed minus 6x. 0 is less than x is less than or equal to 3. A, taking sample points to be right-hand endpoints. And n equals 6. All right, I say all that out so you'll know. I think that's what they kind of do in the book. So, no, we'll get back to that. We're not back to the handout yet. I'll click it over to the other screen here in a second to do that. Well, what does this mean? I want Riemann sum with sample points as right endpoints n equals 6. Also known as what? Isn't that R6? Yeah, a Riemann sum is exactly the same thing we were doing. We're just now calling it a Riemann sum. It's the sum of the rectangles from 0 to 3 with 6 rectangles. So I'm talking R6. This is R6. I want to do R6. Okay, well, R6, I need my delta x. What would delta x be? 3 minus 0 over 6, b minus a over n. It's 1/2, 0.5. So each of the rectangles is going to be 0.5 wide. Since I'm doing right-hand endpoints, I might want to go ahead and list out x sub 1 and all that. Draw it out if you want to. What would x sub 1 be? Well, x sub 1 is the first one after the left-hand endpoint, so that would be 0.5. x2 would be 0.5 plus that, we've 1. x3 is 1. Is everybody with me on that? Yeah, x1, see I'm starting at 0. Then I'm going to in half increments. So x1 would be 1/2. That's what I'm saying. Then x2 would be 1. So on and so forth. Okay? So what's R6? Well, it'd be 1/2. The First rectangle would be a half times f of a half. Second rectangle would be a half times f of x2 would be 1. Right? With me on that? All the way out to 3. Calculator? Oh, summation? No, I don't know that one. There might be a way. But, yeah, I think it's that one's something else. I think it's data. It's data points, something like that. So I don't know that there's one that's connected to the functions, and so no, it's just pretty much using the y1. Plug your y1 to be x cubed minus 6x, and then you can do the vars and all that good stuff. So let me do that. Has everybody got it already? Oh, okay. All right, so it's a half times all those, so it'd be y1 of 0.5 plus y1 of 1 plus y1 of 1.5 plus y1 of 2 plus y1 of 2.5. So we got it? Yep, that's what I got too. Negative 3.9375. That's R6. Okay. Let's think about what that means. This is R6. We get a negative value. How can that be? Well, if you look at the function, what does the function look like? It goes up, but then it actually at 0 it comes down here, and then it between 2 and 3 it goes across the x-axis. So yeah, this I'm going 0 to 3. I'm estimating this area and this area, right?